Right. Yay, slides. Okay. Ready to get going? All right, so you just were listening to a band called Black Tiger, which you've never heard before, because it was unreleased, and the song's called Don't Look Back. So don't look back on your monolith as you go to microservices. So I helped write that song about 35 years ago. That was when I was in college band. And then we have a few MP3s of slightly crappy recordings of it. Anyway, so this is trying to just set you up here for this afternoon when Russ will be playing live guitar on stage, because he does that. So just don't miss Russ this afternoon. Anyway, so this is interesting for me. I finished writing these slides this morning. It talks about code that was written yesterday during some of the presentations. I planned on doing it all over Christmas and didn't quite get there, so it got done at the last minute. What I wanted to do was talk about something, since this is one of the sort of conferences where we all, I assume that everyone already knows about microservices. I wanted to talk about something that would be new and interesting and sort of push the boundaries a bit. So this is really a research paper. I did post the slides, I tweeted it, so slideshare.net/Adrian Cockcroft. These slides are up there. If you find any bugs in my Go code, then you can point them out to me. All right, so first of all, introduce myself a little bit. I work for a venture capital firm called Battery Ventures. It's a 35-year-old firm based in Boston, Tel Aviv, and Silicon Valley. I'm based in Silicon Valley, so we have an office in Menlo Park, another one in San Francisco. And I obviously do that due diligence stuff, helps portfolio companies with scaling and moving to microservices and all that kind of stuff. Network with interesting people, that's all of you people today. So by definition, you're in the audience. So part of my job is to just build an interesting network of people that might want to do startups, or might want to work at a startup, or might want to buy stuff from a startup, or all those kinds of things. Tinkering with technology is mostly what I'm talking about today. I'll get onto that in a second. And then I'm on the program committee, and I do lots of talks at conferences and things like that, and have relationships with a number of vendors, things like that. All right, so I'm going to go straight into one of the challenges for microservice platforms, and one of them is managing scale. And you have this sort of, it's not just a large number of machines, that these things come in a hierarchy. So you might have your system spread over multiple continents. There's lots of regions and zones and thousands, and there's potentially tens of thousands of containers flying around, and that's actually not hard to do. This is not a difficult problem nowadays. If you want to deploy something on ridiculous scale, you just have to, there's off-the-shelf code that will do this, right? It doesn't mean that, not every application needs it, but if you need to go to ridiculous scale, all the parts are there to do it, and then you run into some sort of problems of just trying to track everything and keep up with it. And one of the interesting problems here is, how do you figure out the flow across systems? And there are a few tools around. Netflix have built this tool for trying to, that sort of shows all the traffic between different services. There's a Twitter Zipkin thing at the bottom right there. And at the top there's an App Dynamics flow. And App Dynamics I used quite a bit, but it sort of ran out of capacity when to render things when I got to sort of 500 microservices and 10,000 machines or something. So it works really well at smaller scale, and that's fairly typical of most of the user interfaces. And the App Dynamics people hate me using this, but that thing at the top right, that was what App Dynamics showed our entire architecture looked like at one point. They have improved it a lot since then, but that's kind of the problem. That's what Twitter's architecture looks like. That's what Halo's architecture looked like, and Gilt. And the problem is, 450 microservices with an upward, at a point in time that was a year or two ago. I think Uber 700 microservices as of last week. You have to date stamp anything you ever hear from Uber, because they're adding 200 engineers a month or something. Most of the company's been there less than 6 months in terms of engineering. And Netflix is like over 1,000 microservices now. So the number of microservices is basically how many engineers you have plus time, because you just keep making new ones, and the old ones just sit there, and occasionally you turn some off. So there isn't a golden number you should have. It's just going to increase. So one of the things I was interested in trying to figure out how to help people visualize these. And if you're trying to generate data to stress a monitoring tool or a visualization, you have to have a way to create something that it can visualize. And of course, we have cloud, so you can just start up 10,000 machines on AWS and monitor them, which is fine if you've got a really big budget, or you can run them for 1 hour or something. But if you actually want to try and generate something at really large scale that's distributed all over the world in interesting ways, it's expensive and hard to do it. So I built this microservice simulator, which I called Spigo initially, but it's actually sort of being renamed gradually to SimianViz, because there's a company called Spigo, and there isn't a company called SimianViz, because I got the domain. So the point is that this is a canonical Netflix-style cloud architecture, AWS architecture. You have a load balancer, that's where the traffic lands. The load balancer's job is to split the traffic across zones and then find machines in the zones to land the traffic on. That's what an ELB does. It's a sort of a DNS layer plus a sort of an HA proxy-like layer that you can't see that's hiding on the system. But that then talks to the API proxy, and Netflix uses Zool as its API proxy. And that job of that thing is to act as a single endpoint that then spreads the traffic over all the microservices behind it and gives you an API virtualization layer. So your API looks like a nice, it's got all the features in one endpoint, but underneath it, those features are implemented by being routed to lots of different services. So I've got all that business logic in the middle. The Netflix project name for it, the canonical starting point for a microservice is Carrion, which is an elementary particle. So the names that I picked for my simulator, I just used the Netflix names for the different pieces. There's no code relationship. They just sort of roughly do the same thing. There's a storage tier as a service over HTTP called Stash, right? So that's the data access layer. So all the microservices talk to the data access layer, and that then talks to a Cassandra cluster. And the reason it looks like sort of 3 branches is that the traffic stays within zones. Once you hit an availability zone, you stay in that zone. And the way your data gets to another zone is you hit Cassandra, and it copies the data to the other zone. So basically, the data replication across zone is Cassandra, and Cassandra's sort of replication factor 3. So that's kind of, this is sort of the LAMP stack, Ruby on Rails, whatever you want to call it, of the Netflix architecture. It's the simplest architecture that fits. The nice thing about this is it's totally scalable. You can build this to be 10,000 machines wide. You can distribute it across all the zones in the world, all the regions in the world, and it will just work the same. So it's kind of, sometimes it's called a scale-free architecture. The architecture works independent of scale. You could have, 2 microservices in the middle of this, or 3 basically would be the minimum, up to 30,000, and the thing would, and you could distribute it into 6 regions. So that's a nice building block, and it's very symmetric. So when you try and draw it, it looks pretty, and I'll show you later on. If we don't run out of time, I'll show you some things. So the code's there. I worked on this most over the last year or so. And I want to actually show you what the code looks like to try and explain what's going on. So I wrote Go code, where each Go routine is pretending to be a microservice, a real one, that's really out there, pretending to be on AWS somewhere. And the channels are used instead of HTTP and TCP connections. Right, so think of a whole lot of Go routines connected together, a whole lot of channels simulating your actual architecture of real machines with real TCP connections. And I have a protocol that runs over that called go-to-call.message, which is a bit like HTTP with a bit of routing protocol thrown on the top. So, and this is written, somebody accused me of writing Erlang-style stuff in Go. So it's sort of CSP-like, communicating sequential process-like stuff. So basically, everything has a listener. You listen to messages, you process the messages, and you stop, and that's it. It's a very, very simple construct. Depending on what kind of message you get, there's a bunch of protocol things. Hello is how you get named. Name drop is part of the protocol for routing. And then you see a put. And in the put, basically, you received a message, and you're just going to put it down to the next level so that you create another message and you actually replicate. This is basically the code that would be in the Cassandra simulator. So when you put something into Cassandra, it does a sideways replicate and makes more copies. So this takes a put, and it turns it into a replicate, right? And somewhere in there you see message.context.newParent. So, and at the top it says flow.instrument. This is instrumenting the flow through the system in a way that's compatible with Zipkin, and I can generate Zipkin format output from this simulator, right? So, and then there's a bunch of other stuff going on. I actually have a service registry and a whole bunch of things. So, what does a flow trace look like? This is the most basic idea. On the right, you have a stash service layer, service data access layer in zone C, and it's putting into a Riak cluster. Riak and Cassandra are actually simulated with the same code because they roughly do, they're all Dynamo type things. So that's that put at the top, and you see it's a US East 1, it's in zone C, and its job is to replicate into zone A and B and send it to US West 2, where it gets replicated into A, B, and C. So this is the flow you see in the back end. And I've just got transaction number 98, so that's the message that's coming through. And you've got span numbers that increment, and then the P in the middle is the parent span, so you can build a tree. So all you do is in every message you pass these three numbers, and they could be explicit numbers, or in like real HTTP type code, rather than my simulator, they're typically GUIDs, and you put 3 GUIDs in a header, and it's like masses of it's big, in fact, compared to what I'm doing here. I'm just sending 3 integers. Or you can send large numbers in there. So this is what's going on. So OpenZipkin is this common format for trace annotations invented at Twitter. Adrian Cole took it over at Twitter and moved to Pivotal. If you saw Matt Stein? He was talking yesterday. Josh Long, not Matt Stein. So Josh Long did a demo yesterday where he was banging away really fast, and he probably missed it, because in about 3 seconds he showed you how you could include Zipkin in your Spring Boot thingy, Spring Cloud thing. Anyway, so he did a slight change so that actually Zipkin, you can post a JSON object into it to create, because normally Zipkin is linked up to your monitoring system and it's continuously updating. As you run, it's collecting trace data and letting you visualize it. The extension was that now you can post a JSON file into it and do a one-time upload, and it basically says, oh, here's a lot of stuff, and then you can visualize that. And this is what it looks like. This is my simulator, my Riak ELB, and then it's talking to the different zones, A, B, and C. And then at the back end, there's all the back and forth copying between the zones that's going on, right? And when you look at it with the trace, you can see, there's a put, and more put, and at the bottom there's 2 replicates. So this is a single region version of that thing, right? So I do puts, and it copies the data to zone. You see zone B down the side here, and then it says C and A are the last 2. So this validates that my code is actually doing what I thought it was doing, right? And this is measuring the actual messages that are flowing through the system, rather than what the routing network is set up to do. And so it's now trivially easy to blow up Zipkin by creating arbitrary large traces and things, because the simulator can just do that, right? So now there's a way to stress test any monitoring tool that you want to plug tracing data into. So how did I define this architecture? This is the input file that defines an architecture. And it's a JSON file that's read into the Go program. This one is called LAMP. It's a LAMP stack, kind of. It's the simple thing. You've got a web server. You've got a web endpoint. Denominator is like a DNS endpoint. That talks to an ELB. Then there's a web server, and then it's got a memcache and a MySQL. It's actually got 2 MySQLs, a master-slave pair, 1 memcache, 18 web servers, and the ELB and the DNS don't actually have a count. They exist, but they're not in a region, right? So, and you can see on the right-hand side the dependency lists that basically refer back to the names, right? So you can just define any architecture. I was one group in the audience when I was talking about, it's like design. They took their thing that they had running in production, and they did a file that described like whatever they'd built. And I contributed the code into the system. So there's a big data science backend system. So that's all you give it. Now that generates that diagram that's top right. You can see the little sort of thing that looks like a little wing-shaped thing. The yellow bits on either side are the MySQL. The green one at the back is the memcache. The little dots in the middle are the carry-on. And there's a sort of rendering algorithm for choosing the colors and the sizes and the lengths and things. Now, you get this file, and then you run Spigo, which is on GitHub. So you just say Spigo, I say the architecture on this lamp, which reads that JSON file in. -J means I actually want to save the graph output as another JSON file, so I can actually render that picture from it. And this says to run it for 2 seconds, which is enough. 2 is kind of the minimum. It takes about 1 second for all of the machines to wake up, all the nanoservices to wake up and find their service registry and connect, and then 1 second to run, and then you stop. There's actually a chaos monkey, which halfway through picks somebody and deletes it. I didn't mention that. So there's a victim here, so the web server is the victim. So halfway through, whatever time span you give it, it will actually tell the chaos monkey wakes up and says, let's kill one of these nodes. So I'm incredibly crude. There's like 3 lines of code doing this at the moment. So you can see it loads the architecture from a file. Starts it up. You can set a scale factor, so I could actually say 200% or 1,000% and just make everything would be, all the numbers of machines would be multiplied by that. I've got a service registry in each zone. Those are the Eurekas. They're started automatically. You don't have to specify them in the architecture. And then you can see it parsing that file. So it's got the RDS, memcache, web server, the ELB, and the denominator, which is the DNS. And you can see it read those in. And then the denominator, the endpoint, is told to just generate traffic. And basically, every 10 milliseconds, it'll launch a message, a get message or a put message, and that will flow through and exercise the system. It's just random routing. This is not simulating a real machine very well at this point. If you look at the timestamps, you can see 1 second later we get the chaos monkey delete, 1 second later shutdown. The tooling code that actually automates and sequences this is called Asgard. It has nothing to do with Asgard or Spinnaker. It's just like I needed a name for that package. And I copied the Netflix one. Then you see the service registry shutdown, it closes, so that's it. And that's a typical run. That generates all the stuff you need for different architectures. Here's a more interesting architecture. I did this for the Riak conference, Recon, and they had published an Internet of Things reference architecture for Riak, with taking into account their new Riak time series and the Riak key value. So I thought that would be interesting to do. So it's a bit more complicated. You can see I've got all the names and stuff in here. And when you render it, the output when you run the thing with -J is a JSON graph file which describes all of the nodes and edges in your architecture. And that's when you do that, it looks like this. Let's just go through and annotate this. So think of like a Nest thermostat. There is an ingestion endpoint that the thermostat is talking to. It runs that thermostat protocol. There's also an endpoint that your iPhone is connected to so you can see what the thermostat's doing, and that's the stream endpoint. It's streaming past the current latest values of things, so you can see that on your phone. And then once a month, Nest sends you an email saying, hey, this is what your usage looked like for the last month, so they're doing a bunch of analytics. So at the back end, there's an analytics endpoint that is basically being used to generate messages that are sent out more infrequently or summarizing things, right? So that's this is a very generic kind of pattern you tend to see in Internet of Things. You typically see these 3 types of endpoint. There's an ELB load balancer for each of them. There's normalization, stream, and analytics services providing those endpoints. And you can see it sort of grouped in pairs. It's hard to see here necessarily, but this is spread on 3 availability zones in 1 region. That's what I'm modeling here. And then there's a message queue, because that's what the architecture they had, and there's a Riak key value store at the bottom. There's another message queue, and a RabbitMQ kind of things. And then there's a Riak time series there, and an ingester service that ended up in the middle. So that's all fine. But then when I can run this, I generate this by running Spigo once, and then there's another option on Spigo that basically says, I'd like to do 2 regions version. So I'm going to do US East and US West. And when you do that, it looks like this. It generates a graph that looks like this. The endpoints are these, because they're sort of set up to be DNS, the idea is this is a DNS splitting endpoint. It's an endpoint you hit, and you program DNS to be location aware, and if your traffic is coming from the East Coast, it sends it here. If traffic's coming to the West Coast, send it there. So typical globally distributed web services work like this, right? There's various ways of implementing it. It's the way Netflix works, the way lots of people work. Then there's a West region and an East region ingestion system, because your thermostats basically in the West region aren't going to move around very much, so they're just going to stay there probably. And then when you get to the back end, it's a multi-region cluster for the analytics. So you get that big circle there because they're all connected to each other. When you do these distributed data clusters, everyone talks to everything, and when you render it, they all get clumped together in a circle. So that's all fine, but then I have a new question. This is some slides I've used before. So my new question, what is the response time of the stream endpoint? How could you figure that out? Right? And reasoning about response times of really complex architectures is a hard thing to figure out. But it's a good question, it's just there isn't a good answer for it. You could go build it and try and measure it, but what I want to do is try and figure out some tooling to help model and measure that. Right? So let's talk about response times. So let's go to a simpler service. This is that LAMP stack thing, right? BLB, web service. Okay, if this is that, what would you expect the response time of a system like this to look like? Like, what is driving its response time? Right? Still a bit complicated? All right, let's go for an even simpler one. Okay, this isn't even microservices now, right? I have a load generator, I have a web service, it has a MySQL, a memcache, and the MySQL has a disk volume, right? Okay, so what would you think the response time of this would look like? Like, if you're looking at what the distribution look like, what would drive that? Well, there's obviously the CPU time it took to get through the web service, right? Whatever, a few milliseconds for that. There's the MySQL time, and there's some memcache time, and then sometimes the MySQL has to talk to disk, right? But when it has to talk to disk, it probably takes a lot longer, right? So, but it doesn't always talk to disk. So there's sort of something like a cache hit rate for how often, when you ask MySQL something, did it go to disk versus getting it out of memory? It was, lurking around in the SQL cache, right? Result cache, whatever MySQL calls that. But there's a memcached here, so some of the time you look in memcached and you find it. So that would be really quick, right? So if you think about the response time of this system, you've got probably a MySQL cache hit rate, and you've got the response times, the time it takes to do the web service bit, the time it takes to look something up and get across the network to MySQL, get across the network to memcache. There's these pieces, right? And if you sort of measured all of them independently, you could add them together somehow to find out what the final thing should be, right? So if you know that memcaches always respond in so many microseconds, and MySQLs always take this number of milliseconds, and right? So, but how do you add it together? Have you ever tried adding together response times? It doesn't actually work because there's a bunch of random fluctuations in there, and you can't actually add together the average response time. And if you do the max and min, that works for a small number of things. It's like the max of the worst case analysis. But as soon as you get a complicated system, it goes to plus or minus infinity because like the tolerance stack up is everything. Like the possibilities are you could get anything out of it. So this looks like an interesting problem. Like, how do you add together distributions? And it's a problem that has been solved in other domains, and it's called tolerance stack-up, and mechanical engineers know how to do this. It's a well-known technique, and it's also something that's been used in financial modeling. Like, if you're trying to predict something like what should your risk analysis and those things. And it uses, the normal technique is to use Monte Carlo simulation to do this. And some people get a deer in the headlights kind of look when people say Monte Carlo simulation. So I'm not going to explain what that is. I'm going to show you that there's an easy way of using it. And I wrote the abstract for this talk and that crap, and I have to figure out how to do Monte Carlo simulation in Go. And then I was worrying about this, and then on New Year's Eve, somebody tweeted, hey, look, there's a new Monte Carlo simulation free spreadsheet thingy. And I went, oh, good. Figured it out, found the guy that wrote it, started little chats with him, and he needed to add a couple of things which he added last week. And this is what this is. So this is, okay, so this is that. Okay, load generator, web service, MySQL, memcache, disk volume, modeled using a spreadsheet with a distribution simulator in it. So this is a model. You can get to this at Guesstimate Models 1307. It's a public model on the site. And Ozzy Guin, who's a developer, I guess he's Dutch probably from his name, but he lives in San Francisco, is just like, he's had thing in his head that he wanted to build this thing for the last year, and he finally built it, put it out on the internet thinking it would just confuse everybody, and it's had a massive response. He got very busy, because everyone thinks this is really cool. And there are lots of models here for like predicting stuff. Someone did a model for how long it would take to take down their Christmas tree. You can do anything on this. But this is that model, so you can see the different bits. So I'm going to zoom in. So this is the memcache bit. So a memcache response time, the one in the middle should say network. So let's say it's 230, whatever, microseconds is the total response time. You spend 160 microseconds going back and forth on the network. I made up these numbers, it doesn't matter really. And then when you get to your memcache, the CPU time is 65 microseconds. But they're not just fixed numbers, they're plus or minus. And right now the thing supports, you can kind of see a shape on there, right? It's what you put in two numbers in a bracket, it creates a normal distribution with those as the 90% and 10% points and gives you a spread. So if you've got a very fuzzy estimate, you give it a wide spread. If it's a very accurate thing, you can do a point estimate or you can give it a narrow spread. And what this is doing is it's taking 160 and 65, and it gets you to 230. And because they're normal distributions, it actually does add up nicely. And you don't really need to have the distribution analysis to get the same answer. But the real numbers, it would be a skewed distribution. It would be a one-sided thing, because you don't have a negative response time. Response times usually start somewhere, and then they have a long tail going out to one side. So because they're asymmetric, when you start adding together asymmetric distributions, you really have to use this tool to do it. He's still adding some distribution types on there, but we'll get to that. And down the bottom, I've got the memcache hit rate, which is the number sitting in the thing. And you can see there are arrows pointing here. So this thing on the left is a formula that basically says that one and the two on the right are added together. And down here is my MySQL. I've got a 70% hit rate with MySQL. It's got some CPU time. There's a disk, which is nice and slow. Probably an SSD, but still, it's 750 plus or minus 460. I give it a nice broad response time. There's the same network traffic time to get there. And there's my MySQL response time. And if you can actually see this very well, I'll put up better, but there's actually a big spike and a flat spike, right? I'm adding together a very broad distribution and a very spiky distribution, and I get a multimodal distribution. It's got two spikes, and they're in different places. And then the final thing I've got up here, I'm adding them all together, and you can actually see, hopefully, there's three spikes here. There's the MySQL spike and the others, but I can zoom into that. You click a button, that top right button, and you get this is a pop-up. Right, this is a lot easier to see. That's the same number. You see the 620 plus or minus 670. I'll get there in the end. Right. This is the same data. So now you can see the first spike is my MySQL cache hit rate. The second spike is my memcache. The first cache is memcache D. The second one is MySQL, and the big broad thing is I had to go to disk. Right. Now, if you look at this, there's some percentiles. You've got the 99th percentile. If anything changes, like a cache hit rate changes slightly, the way this changes is that the 99th percentile will change quite a lot. But what happens to the shape? So what we've got here is three modes. This is the formula, which is my service CPU time, which just is a standard add-in. And then you have to basically do some funny things to select between things. So this random int thing is a bit of JavaScript. This whole application is built in the browser. It was written in JavaScript. Anyway, and you can do question mark, colon, things to select. So that's the way you combine distributions is with this question mark, colon, and choosing random numbers things. Anyway, so that's one, and this is 40%, 70% where I started. Now, this is what happens if you do memcache 60% hit rate. You get a much bigger spike, right? But the spikes are all in the same places, and the 99th percentile changed from 1500 to 1480, okay? And then, yeah, so it just changed. And then here's one where I made MySQL, memcache miss a lot and MySQL hit a lot, right? You see that the distribution keeps changing. So this is the simplest system, and I've got three modes. Right? Think what a microservice is like, where every service has its own distribution, and when you're looking at that IoT endpoint, you're looking at potentially the contribution of tens or hundreds of services, all of their individual response times all being added together to give you a thing with lots of modes in it. Right? It isn't a constant average. You can sort of average it out if you want, but you're losing a lot of information. You can actually see what's going on. So this was just generated by hand in the tool. So this is just me playing around with that thing. I just created that by hand. You can generate anything you like in that spreadsheet. So I've got a simulator. I've got a spreadsheet. I have to connect the two. So earlier this week, Coda Hale accepted a pull request from me. I was very happy about. And now HDR Histogram has the ability to dump out the distributions directly. The underlying distribution can be saved. And I was talking to Peter yesterday, and then he wrote some code overnight, and we haven't fully integrated it. But I'm using currently a hacked-up version of GoKit metrics, and Peter's done a fixed-up version. So this is like code in progress, basically, today, roughly. And I've implemented this in my system. So I have a client, I have a server. They both have their own notion of time. And you get a request from the client to the server and a response from the server back to the client. And the way Zipkin instruments these is with these codes, CS, SR, SS, and CR, right? These are annotation points in the Zipkin end-to-end flow system. So every time you send a message from a client, you do an annotation, say this is a CS annotation, you just put a high-resolution timestamp on it. And you do, when it lands at the server, you drop an SR. So you have a network of these flowing around in your system, and Zipkin logs them out and does those diagrams that I showed before. So what I did was I said, well, I want to do a bit of measurement here. So I'm going to calculate a response time from the client's point of view, which is CR minus CS timestamp, and I'm going to calculate a service time that I can, from what happened on the other end of this request, which is shorter, SS minus SR. And then I can actually measure the network latency, how long it took to get there. Now, my simulator cheats. It's a distributed system with a single clock. This doesn't happen in the real world. Clocks are always offset. So you can't actually do SR minus CS because they're on a different time base. Like your high-resolution time be offset. But it turns out if you do the round trip, the error cancels out. Right? So if you want to measure round trip time between two machines, you can actually difference these endpoints. It's because if you look at that calculation at the bottom, SR minus CS plus CR minus SS is actually those two arrows, the smaller arrows. But you can rearrange that to be the difference in time at the client minus the difference in time at the server. So there's a stable metric there. So just a little trick. Don't like different time bases that aren't the same thing. So I wrote some code. This is the denominator thing, that endpoint load generator thread. Remember, so it looks very similar. I have the listener, I select, I instrument, and I send a message. I send down at the bottom, actually, it wakes up every 10 milliseconds. So if you look at the bottom here, the chat ticker, it's sending a message and it's setting a GET request. It's just asking why. It just sends why. That's its query. There's no real data in the system. But the message why flows down into the system, and then when it responds, it just sends back because, and that just comes back up. This is really dumb, but it's, I'm just exercising a network here. So I create the outbound message, I annotate it, which is putting it into the Zipkin flow, and then I send it. And I send it to a random dependency. That's what there's a little way of just picking someone random to talk to. When it comes back, it's my GET response. So it comes back. All my messages come in at the top of this model. It's like an actor simulator kind of thing. So I don't have responses coming back in where I sent the request. I send a message, and later on I receive a message. So I have a GET request message, and I get it somewhere deep in the system, somebody sent a GET response that flowed back up. So I do a flow.end, which basically captures the annotation to say this flow ended, and I want to collect all the data about it and store it. And then later on, when I finish my run, there's a goodbye message comes to this thing that shuts it down, and it actually saves all the histograms of the different, the network time is the time it took for a message to arrive, plus the response service and round trip. And then I save all of these guesses, so I'll show you what that looks like in a minute. Right? And then I basically, if you send somebody a goodbye message, they have to tell their parent that they're going away, and they sort of just quit at that point. So there's a supervisor model here. The parent is the supervisor process that watches all of the underlying things. Okay. So in GoKit, this is the code. If you're writing anything in Go and you want to just use the metrics part out of GoKit. That's all I'm using. So this is the standard thing. So I've got a couple of metrics there. I want to create a new histogram of my own, and I use metrics.histogram is what I return, and I set up a histogram that's got a minimum of 1 microsecond and a maximum of 1 second, I think. No, a millisecond or something like that. It's 1,000 nanoseconds, 1,000,000 nanoseconds, yeah, 1 millisecond, because everything happens in the simulator in microseconds, right? You probably want larger numbers in the real world, right? And then basically it's very simple. You create the histogram, and then I'm actually collecting the first 500 samples that get put in the histogram in a buffer, so that I can send that out to Guesstimate. And I'll show you what that looks like later. But you could make that number bigger if you want. It's enough. It's sort of the smallest amount that will generate some kind of distribution. And then every time you get to something, you just do measure, and it just puts a time duration in the histogram, and I just do a bit of clamping. So this is very simple code, equivalent to how much work you would have to do to add this kind of instrumentation to your application. That's what I'm trying to show here. Now, once you've collected all these histograms, I have a thing, and there's a better version of this in the new Go kit using, was it Terabyte or something? Yeah, but I hacked it up because I didn't know Terabyte. So basically, each histogram, at the end of the simulation, it writes each of these to a file, right? It's a CSV file, so it dumps it out. And if you zoom into the top part, you can see it has a name, which is the name of the load generator, and the storage is the architecture I was running. It's got 1,978 samples that were counted, and I've got a 50th percentile and 99th percentile. Those are the times at the 50th and the 99th. You can add as many of those as you want. If you look at the previous thing, that little array at the end, int 50, 99, you can add as many percentiles as you happen to feel like collecting. It just dynamically adds them in here automatically. And then you see the numbers. And as well as the from, to, and count, I've got the probability, which is normalized to 1.0, right? Like probability distribution, and then this sort of bar thingy that basically gives you a bar chart so you can see what's going on. I just sort of ASCII art, right? And then because I'm actually skipping all of the bars that are 0, I use a colon instead of a vertical line to show you that you're skipped. You can see that they're non-contiguous. The first two bars, the 2 point, it doesn't match the next from. And once the 2 does match the next from, I go to things. So it's just a few visual cues, right? Just trying to make it easier to see. Then to drive Guesstimate, this is actually, you have to have talk to Aussie and get access to the alpha version or beta version or something to make this work right now. But this is the object that Guesstimate wants to match that, right? And this is actually a test one. So you have to send it this JavaScript object, and in particular, see it says Guesstimate's metric data. There's a whole lot of numbers there. That's a bunch of samples. That's those 500 numbers I collected that I stuffed in my histogram. But for Guesstimate's point of view, I just want to create a buffer with those numbers in. And this is just a sample. This is the test per code that I've got. And there's 4 different types of things. You can see my memcache, my CPU, and things like that. And then down at the bottom, I can do points. 40 is a point. I've got the normal distribution, which is 1,000 to 4,000, so it basically creates a distribution centered on 2,500 with a certain width. And then the formula, right, which you saw the formula earlier on. So this is how you feed that spreadsheet, which is all written in JavaScript and runs in the browser, right? And when you get that and you post it into Guesstimate, you get this, right? At the bottom right, you see that little diagram. There's dash CPU, the percentage, the formula's hiding in there, right? That's the formula at the bottom. The other thing is those letters AE, AC, AD. Those are used when in the formulas. They refer to different cells. And if you zoom in on it, you can see this is the actual distribution of data that was collected by that thing. So you've got it's a one-sided distribution now. It looks much more like a real response time. Right? So now I've figured out that. So the code, I needed to have some code to generate this file format, right? So I wrote it, most of it yesterday morning in James Lewis's talk. And posted it, created a new repo on GitHub, and I have a new project on GitHub, and it's called Go Guesstimate, and it's pretty dumb, but it actually worked. And So this was just this is what you get when you run the Go test piece. It actually generates this file, which you can dump in. But then when I run Spigo itself, I get a lot more histograms, and this is actually generated by Spigo with the -C option to collect monitoring data and flow data, and it wrote out a whole lot of these histograms, and I think I got this working yesterday afternoon at some point, at some point yesterday afternoon I got this working. Conference-driven development is a thing, right? I have deadlines. I don't have a delivery other than conferences. So there's the histograms. I don't currently have the names, but there's a change in GoKit where I can extract the name of the histogram so I can actually see what's going on. And then I need to stitch them together. So there's a few things still need to be done, but that's basically it. All right. So I'm going to do a couple more things, and I'll show you actually some of this, what this looks like live, right? So a bit hacked up, but real time. Interesting stuff. So I just want a couple of things that I want to talk about generally about what's going on in 2016, and then I'll try and get some live demo stuff going for you to show you what this looks like. Two things that I think I'm starting to see bubble up. One is serverless architectures, AWS Lambda. There's a toolkit called Serverless. There's another one called Apex. People are starting to build tooling on top of Lambda for building things, and I'm starting to see a little bit sort of the first signs of some sort of startup activity around this space and some tooling. So I think that's interesting. And the other thing is, like, if you're on microservices, you have to immediately go to the exact opposite extreme in Teraservices, right? Terabyte-sized services. So this is just kind of mentally thinking, well, if something gets interesting, what's the extreme opposite look like? I just have a natural instinct to do that. So. If everyone's looking one way, I'll look the other way. I'm one of those people. Why are they running away? So what can you do if you have terabytes of memory? You can engulf your entire data set. You can do graph databases that you don't have to partition. There are some memory-intensive workloads where the CPU is idle, but memory is full. So there are some times when you really, memcached, almost always idle CPU. Having ridiculous amounts of memory would help. Some of these systems, you can buy machines now with terabytes of memory, and they cost millions of dollars. They are available, right? But in real life, you can't get one to go play with your open source project. And then some of these things are becoming non-volatile. So if you have terabytes of memory and it becomes non-volatile memory, that gets really interesting. Basically abandon most of the computer science research of the last few decades, because they all say, oh, I'm optimizing for spinning disks and saving stuff out of memory. No, you don't need to. You don't need file systems and databases anymore. You just have stuff in memory. A couple of options for this. One of the portfolio companies I've been working with makes a DRAM and flash combination model where you get a DIMM with 256 gigabytes of memory, one DIMM, instead of the usual 16 or 32, and you put a bunch of those in a machine. And they have a toggle where they are normally configured to be non-volatile. They get wiped every time you boot, but if you do a BIOS upgrade, you can run it as volatile. And then Amazon announced last year, they're going to have an instance type with more than 2 terabytes of memory. That's what I think really unlocks the innovation, because now if you have a startup or you're playing around with an open source toolkit, you can basically go, well, I wonder if this thing scales to 2 terabytes, and for a few dollars in 1 hour, you can run it. And then you shut it down again, because that machine's going to be pretty expensive by the hour. But you can probably afford it for, it's probably cost of lunch or something like that. I don't know what it's going to be, but it's comparable to the cost of, the most expensive instance they've got right now is, I think, about $3. I have no idea what they're going to charge for it. But it's certainly not going to be $1 million. It's going to be a few dollars an hour. And this, I think, is going to unlock a lot of innovation. This is what that memory DIMM looks like. You don't even have to change your BIOS. You just plug them in, and the way it works is you put, a typical system, you put in 8 regular DRAM DIMMs and 8 flash DIMMs, and what it's doing is shuffling data back and forth. It gives you most of the performance of DRAM and most of the capacity of flash. And it actually works. The benchmarks that have been going on, it's actually working quite well. All right, I'm going to do a bit of Q&A. The last slide here is like the word from my sponsors. These are some of our portfolio companies that you might have heard of. All right, so I'm going to I'm going to mirror the displays. Okay, hopefully this is working. And pull up this thing, and then go. All right. So this is that Riak thing, and it has this very satisfying sort of wiggly, it's a thing that it does. Basically, it's this is a local thing. It runs on my local machine. It just has a copy of the D3 library in the file system. It picks it up. This file is shipped with the thing. So you don't need anything. This is if you want to just go hack at the parameters, this is everything in one file. This is Adrian's first ever JavaScript program. I read a D3 tutorial book. I ended up with this, right? It's got, you can pull things around. Then you just change the name, and there's like a bigger one. This is that, remember the double one? And then you can give it more charge. You can every time you give it a charge, it kicks it a bit and spreads everything out, right? And then there's another one here that I doubled the size of the thing. So this is a 200% sized one, so it gets a bit slower at this point, you see. All right. And you can just wiggle these things around. And anyway, they look like jellyfish. They're called jellyfish diagrams, so they get wiggly things. All right, so that's one. Then I did this at a conference a year ago, and there was a bored front-end UI developer in the audience who took one look at my JavaScript code, vomited all over it, sent me a pull request, and I made him a committer. And then he got busy. I helped him find a job, and then he stopped working on my open source project. So just putting that out there. So this is his, it can be helpful, but, he's fine. He basically refactored, and he built me this single-page app, which is built, it's got React in it, and it's actually much faster. So this is that lamp stack. This has got a few extra tricks where you can hold it there. You can actually double-click on something, and it disappears. I don't know why we did that, but this just seemed like a good idea. It's like Chaos Monkey. Click. Ah! So you can be the Chaos Monkey. Then this is... and then this is there's a bunch of different architectures you can pull up here. These are all the basic ones. The migration one, the idea of this was it shows you how to migrate, and you can see this is just running locally. You have to do an npm install and a bunch of junk like that to get it to work. All right, so this is a lamp stack, right? There's your ELB. There. This is basically the same design as that last one I looked at. Now, the first thing you're going to do is add memcached to it. So let's pull this out so you can see it. That's the one with the memcache, right? Because that sped you up a bit, but that's not really microservices. So, and then you add an API proxy. So let's drag this thing up. So this one now, you see it's now got zone-aware routing. This is your proxy in zone B, right? There's your PHP code, because you're a monolith. There's your MySQL, right? I call my monolith PHP. It's just a thing. I don't know how to write code in PHP, luckily. So then I've added in the back end here, I've now got data access layer, right? So now this is my old code, but I've changed the code so that it's doing REST calls to data access layer instead of SQL calls into MySQL, right? That's the first level of abstraction of picking that's the first time you change your code, but you're now breaking a monolith away from the ORM being locked into the database model. And now you can start adding microservices in the middle. So let's do that. Just to make Richard happy, I think I have PHP and zone. Oh, I got Node in there now, so Richard Rogers, make him happy. All right, so now we've got Node and PHP. So sandwiched between the data access layer and the API proxy, you can start slicing things up and adding more microservices. So the next thing you do is add a Cassandra cluster, and then you get rid of, what are we doing here? Oh, we get rid of MySQL. Eventually, and then we have 2 Cassandra clusters, and then we have 1 global Cassandra cluster, and then we add more regions, and it sort of floats around, and it gets gradually slower. I found another graphing library that does more, but this is, I think this is, I forget how many zones this is. Anyway, you can go play with this. You used to be able to run this thing off of the web by just clicking a button, but it was hosted on DivShot, and DivShot shut down in December, so that should get fixed soon. So I'm out of time. I'm around for the rest of the event, so is there any time for a question or two? Or are we done?
We have a minute. So
1 minute, and we'll get a question. We've got microphones. Any more questions right here? Hopefully this was useful or interesting.
Nice experiment. Thanks for your talk. Did you also verify this with actual measurements for systems, maybe compared to scientific papers that produce distributions of response times, etc.?
Not really. I've seen systems, I've measured response times of systems and seen these kinds of effects before. The simulator doesn't try to be like, it's not really a cycle-accurate simulator in this. It basically simulates the right topology and some of the right behaviors. The thing about simulators is the stuff you decided not to do is important, right? So you can express a microservice architecture with it, and you can generate metrics, and you can fake the numbers coming out of it any way you want. Right? You can pretend you've got CPU time measurements coming out of it. You could pretend you ran out of memory somewhere. Because the idea of it is monitoring tools look through an agent interface into the real world. And if you connect to that agent interface and feed made-up numbers into it, the monitoring tools can't really tell that it's made-up numbers or a real system. So what I'm trying to do is provide a framework where you could go and build a monitoring tool exerciser that could create arbitrary scale or whatever complexity you want. And what I've been doing so far is just adding flow simulation, and this response time histograms was sort of it was bugging me, and I thought it would be something good to talk about here, because I think that understanding the distributions of response time in these microservice architectures. So I'm just basically trying to show these techniques. Right? The actual response time distributions you get out of my simulator are, what you'd expect if you have a bunch of Go routines running on a laptop, really. It slows down pretty quickly. Okay, I think I'm out of time. Okay, well, thanks, everybody.